Uno, dos, tres, cuatro.
Hi everyone, welcome to an introduction of logarithms. Logs, if you want to think about it, would be something that we're in pre-calc 11, probably before then. It's one of those terms you've heard. You've heard of what a logarithm is, or you've heard about a logarithm, but you don't know too much more than just the name of it. And so we'll start today with an introduction to logarithms. And to best introduce logarithms, we first need to review exponents and take a look at some of our exponent laws because they tie into logs because they're directly related. So let's get started and let's see what we can recall from exponents. With exponents, we have the product law. The product law would say x to the m times x to the n equals x to the m plus n. Another way of thinking of it is if you had something like x to the 3 times x to the 4, we know that equals x to the 7, where you could add them up together because you have 3 x's times by 4 x's, so in total you would have 7 x's if you multiply them together, x to the power of 7. The quotient law would say x to the m divided by x to the n equals x to the m minus n. And so if you think of an example of that, if you had x to the 5 and you divide it by x to the 2, you get x to the 3, and we could get x to the 3 because you would have 5 x's on top and you divide it by 2 x's on the bottom, and you're left over with x to the power of 3. The power law could say something like this: x to the m taken to the power of n is x to the m n. So if you have something like x cubed and that's all being squared, you're going to get x to the 6, and you could think of that because you have x times x times x happening twice. So then in total, you would get x to the power of 6. The power of a product, this m can get distributed. So you'd have x to the m times y to the m. And another way of thinking of that is you could say something like, well, if I had x times y to the power of 3, that's going to equal x cubed y cubed, and that's because I have xy times xy times xy, which would say I have an x times an x times an x equaling x cubed, and then a y times a y times a y equaling y cubed. So you guys get the point. The power of a quotient law would be x to the m over y to the m. This m on the outside of the bracket belongs to both the numerator and denominator. So if you had something like, let's say, x over y to the power of 3, we know that that becomes x cubed over y cubed. Finally, if you have a negative exponent, you can do what we call, I don't know if you guys remember that song by Missy Elliott, where she says you got to put your thing down, flip it, and reverse it, kind of out of the blue. So if you have x over y to the power of negative m, you can, I don't know about putting your thing down, but then you can flip it and reverse it, and then as Missy Elliott would say, that's how you work it. So you'd have y to the m over x to the m. Okay, so whenever you have a negative exponent, you would flip your base, and then based off of that, you could change your negative exponent into a positive exponent. So how does this all play into what we're going to be doing today? If you take a look at these bases, each of these questions, of these 5 examples here, could be solved by using logarithms, but they could be solved easier without using logarithms and just by being able to use what we know about exponents. So thinking about example number 1, if the left side is equal to the right side and they each share a common base, they both have a base of 5, then we can say everything on the left side is equal to everything on the right side, and if they have the same base, then that must mean that this exponent is equal to this exponent. And so that means that you could say 2x plus 3 is equal to 7, and you could isolate for x, so you could subtract 3, and x would be equal to 2. You could do a substitution, put 2 back in the top, and you'd find that the left side would equal the right side. But basically, the best way to do these sorts of questions is if they look like they share something which you could either you already have the same base or you could create the same base, then you want to try to do a method that wouldn't use anything beyond exponent rules. Looking at example 2, you would see you have a 7 as a base and a 49 as a base. So now we don't have the same base, but they're related to each other. And you could easily rewrite the 49 in terms of a base of 7. 7 squared would be equal to 49. So if you rewrite this and you say 7 to the power of x minus 2 equals 7 to the power of 2, then you could say, well, because they have the same base and they're equal to each other, then I can compare the exponents with each other. So you could say that means that x minus 2 would be equal to 2, so x will be equal to 4. If you feel like you got the hang of this, and you might want to try the next few by pausing the video and going ahead. Otherwise, I'll just keep going through them. With 3 and 81, we can make the bases 3s. Usually making it a smaller number is easier than trying to make the 3 into an 81. So we could say we have 3 to the power of 5x minus 1 equals, and then instead of saying 81, you could do a factor tree and figure out what that would be expressed as a power of 3. We know that's 9 times 9, so it'd be like saying 3 squared times 3 squared, and that just is 3 to the 4. And so we'd have 3 to the 4 raised to the power of 3x, which is the same as saying 12x. And then based off of that, once again we have the same base. Okay, here's my dad joke of the day. And so if you have the same bases and they're equal to each other, then just like DJ, you can drop the base, and you would have 5x minus 1 equals 12x. Okay, I feel like I got a couple smiles out of that, but I'm not sure if I got a full-on laugh. Some of you are wondering, what are you talking about, Mr. Wong? Okay, so if we want to solve for x here, -1 equals 7x, divide by 7, and x would be equal to -1 over 7. Okay. If we have a 27 and a 1/9. This is the first example where you probably don't want to change them to a 27 and you don't want to change them to a 1/9. You want to change them to something totally different. But the 27 is related to the number 3 and 1/9 is related to the number 3. So I would recommend changing them both to base 3s just because that's a small positive integer and that's something that they could both easily be changed to, and then you can compare them and drop the base. So with 27, you could say that 27 is equal to 3 to the power of 3. And 1/9, well, 9 is the same as saying 3 squared. And then instead of saying 3 squared, if it's 1 over 9, then that would be saying that we would have 3 to the -2. Remember that negative exponent means you have to, I'll just do this on the side here. If you have a negative exponent, here you can put your thing down, flip it, and reverse it, and that's how you get your 1/9 there. So what we could say here is 3 to the -2 is being raised to the power of 1 minus x. They share the same base. We can multiply those by each other, multiply those, and we could say something like 9x, 3 times 3x, is equal to -2 plus 2x. And then we could subtract 2x onto the left side. 7x is equal to -2. So x would be equal to -2 over 7. We could sub it in to do a check, but hopefully that worked out okay. Okay, this final question is definitely much more abstract than the previous examples. And with this one here, if you have an 8, a 16, a root 2, and a 1/2, changing everything to 2's would be the most ideal. But even when we do that, it's not going to be super straightforward. So let's rewrite these in terms of bases of 2. So we could say we have 2 to the 3 times by 2 to the 4x equals the square root of 2 is the same as saying 2 to the 1/2. And then 1 over 2 is the same as saying 2 to the negative 1. And that's being raised to the power of 3x plus 2. Okay, so on our left side, we can tidy this up a little bit. On the left side, if you have powers that are being multiplied by each other and they have the same base, then you can add the exponents. So we could say this could be, well, let's first say it's 2 to the 3 plus 4x. And then over here we could say we have 2 to the 1/2. And then that's going to be, if I distribute this in here, it would be minus 3x minus 2. And now that we have something in which they both have base 2's on the left side and on the right side, we can just look at the exponents and we could say 3 plus 4x is equal to, it's equal to, I'm going to say 0.5. I should say 1/2, but I'm going to say 0.5. Minus 3x minus 2. And I'm going to say that because algebraically it's going to be a little bit easier just to try to solve for x here. So let's add 3x onto the left side. We get 7x. And let's subtract 3 onto the right side, and we would get 1/2 minus 2 minus 3, which would be negative 4.5. And then if we divide by 7, x is going to equal negative 4.5 over 7. And I would accept that as a correct answer, but I would also say that's a bit of an awkward way of expressing it because you have a decimal that's expressed in a fraction. And so a better way to do this would be, well, if we times the top by 2 and the bottom by 2, probably be best to say something like negative 9 over 14. If you kept your 0.5 as a 1/2 fraction, I'm sure you got negative 9 over 14 right away, but I would say that would be your best answer. Okay, finally, let's take a look at something like this. Simplify and express the fraction as a fraction in lowest terms. So if we're dividing here and we have a 4 and we have an 8, I think we should change these to bases of 2. So we could say something like 2 to the power of 2. And it's being divided by 2 to the power of 3. And based off of that, we could now say, well, if we're dividing and they have the same base, then we can subtract the exponents from each other. So we could say this is equal to 2 to the power of 2 times 6x plus 1 minus 3 times 4x plus 2. And let's distribute. And we could get 12x plus 2 minus 12x minus 6. And as weird as it is, the 12x's reduce with each other. They cancel out, and we'd be left with 2 subtract 6, which would be equal to 2 to the negative 4. And it says simplify and express as a fraction in lowest terms. So 2 to the negative 4 is our answer, but we know that if we put our thing down, flip it, and reverse it, we could get 1 over 16 is our best answer. Okay, on page 203, question number 1, or questions that are pretty similar to some of the things you've seen. It's just more of an exponent review. And then question number 2, there's some really good questions in there that I think will be just online with everything that we've been practicing here. Okay, we're going to continue on, and if that was more of a review of exponents, I want to do an introduction to logs. And for logs, it's super important to talk about why we use logarithms. Logs are used, if you think back to sequences and series, they're used when doing algebra and you want to solve for an exponent that's a variable. And if you think of all those questions where you had something raised to the power of x and you had to guess and test, or you had to use your graphing calculator, we're going to now be able to use logs to be able to help solve for that algebraically. And what we find is that logs and exponents are actually the inverse of each other. So the best way to talk about logs at the beginning, I think, is to just say, hey, can I find a way to be able to easily calculate some logs in our head? And if we can find a way to be able to calculate logarithms in our head, the first few easily, then I think that you'll gain the confidence. You'll be able to apply it to some more abstract concepts, because logs can get pretty abstract once you build up your rules. So let's take a look at something like this. Example 1, log base 2 of 8. And if you see something like that, what you want to say is this. Your base is a 2. And here's how it's pronounced, or here's how you find it out. 2 to the power of blank equals 8. We could even write that 2 to the power of blank equals 8. Well, what would go in that blank to make that a true statement? And hopefully you could just look at that and hopefully see that that would be 2 to the power of 3 equals 8. And so if you're able to figure that out, then we know that that would be a 3. If you can't figure that out, I guess you could always change the 8 to write it as the power of 2, but hopefully that same process is going to be repeated for the next 5 examples. So our next example, 5 to the power of blank equals 25. And inside our blank would be a 2, so our answer to that is 2. 3 to the power of blank equals 81. 3 to the power of 4 equals 81. 11 to the power of blank equals the square root of 11. That one might not be quite as obvious. And if you're not sure what it is, one thing you could do is you could say this. Well, I know the square root of 11 is 11 to the power of 1/2. So then if they have the same base, then I know that my blank must be 1/2. And so you could always just change the bases, just like what we did in our exponent introduction. Now, example 5, there's nothing there. And if you look up to the top notes, if there's no base denoted, then it's assumed that it's a base of 10. We talk about logs in a base of 10, and you'll see that a lot with our upcoming word applications. So this is just saying 10 to the power of blank equals 100. And we would say 10 to the power of 2 would give us 100. And finally, if you have an x, you could always just say the same statement that we've been saying, because now what's happening is they're not giving us part of the information that we used to have, but they're giving us our final answer. So think about how you would pronounce this statement if you're to pronounce it the same way that you said the first 5 questions. You would say 4 to the power of whatever your answer is, but we know what our answer is. It's 3. So 4 to the power of 3 equals x. So if they want us to find out what x is, it's 4 to the power of 3, or let's just say it's 64. Okay, so what we've really done here is we've done something where we've been going from log form to exponential form. And we are going to make that official in this next part here. So here's an example of a log. Log base 7 of 49 is equal to 2. And the way we would pronounce it is we'd say 7 to the power of 2 equals 49. So if we call this log form and we call this right here exponential form, can we generalize that to something that's a little more theoretical? So if you had log base a of b equals c, we know that our base a to the power of c is going to be equal to b. And that's going to be true for every time you want to go from log form to exponential form. Example 1 and 2, write the following in exponential form? Well, this is just saying 2 to the power of negative 1 equals x. It's not asking us to solve anything further, just can you go from one form to the next. X to the power of z equals y. Okay, so that's our first log law that we've now learned, and we'll take a look at a couple examples on this next page here. So the next part is saying, can you go vice versa? If you're given something in exponential form, can you undo that and can you put it in log form? And it's actually not quite as easy. So what I usually do is I'll write it in log form, but then I'll do a check by putting it back into exponential form and seeing if I had what the original question said it was. So on the right here, we'll say this is going to be log. Well, what was our base? We have a base of 10. So log base of 10. So you would say log base of 10 of 7, sorry, I'm just going to rewrite that, of 700 is equal to x. And you're probably saying, wait a minute, I followed everything up until right here. So let's do a check. Our base is 10, and we usually say 10 to the power of our answer, x, equals 700. And hopefully that makes a little bit more sense and you're saying like, okay, I do understand that. And I'm sure someone's saying, hey, for that 10, do I need to write that? And no, you don't. You could actually just write log 700. So that 10 right there is optional. It's if I was to compare it, it'd be up there with saying the square root of something. We know there's a secret 2 index, but we don't write that. Or if you had something where you have the variable a, secretly there's 1a in front of it. It's those sort of hidden numbers. Okay, so how about our next one here? Our base is a, and so we could say something like log base a of c would be equal to b. Let's do a check of this. A to the power of b equals c. Yes, that's true. Okay, now given that, let's see how we could do with some of these questions. So I would encourage you to try, well, I'd say the first 5 you should be able to knock off, and then some of these last ones are a little bit more complicated, but let's see what we can do to be able to solve some logs. 2 to the power of blank equals 16. 2 to the power of 4 is 16. And you don't need to write this 2 to the power of blank equals 16 or anything like that. As long as you can just say the answer is 4, that's all good, but it might help you. 3 to the power of blank is 27. 3 to the power of 3 is 27. 7 to the power of blank equals the square root of 7. We had a question like that earlier that equaled 1/2. 5 to the power of blank equals 1 over 25. If that's strange, then I would say, well, let's change that 1 over 25 and let's rewrite that as saying 5 to the negative 2. And then you could say that means our answer will be negative 2. I really like this one. A to the power of what equals a? Well, if it's just an a, it's raised to the power of 1. So that means that would be 1. And you could probably now presume a new log law and say, well, if ever my base is equal to this guy right here, and they're exactly the same, then it's always going to be 1. If I had something like log of the base of 117 of 117, it's just going to be 1, just by definition. And you might be saying, if we call this bottom a right here, if we call that the base, what's the term for this? And you know what? For years, I didn't even know what to call it. And I looked it up, and they call it the argument. If you have a better name for it, then please mention that in class. Yeah, technically it's called the argument. So number 10, log of log x equals 0. Okay. definitely a couple ways to be able to go about this question. So I'll show you one way, but knowing that there's multiple ways to do this. Your base right here is a 10, and you could say something like this: 10 to the power of 0 equals log x. And 10 to the power of 0 is equivalent to just saying the number 1. So 1 equals log x. And then our base right here is a 10. And we'd say 10 to the power of 1 equals x. So x equals 10. You might need to replay that a little bit just to see how that worked again. Basically what happens is if you have a log of a log, then you're going to have to put it into exponential form 2 times. And if you had a log of a log of a log, you'd have to put it into exponential form 3 times. If you want to do a quick check to see does my answer make sense, I bet it will. If you put 10 in for x right there, log 10 is just the number 1. So now you would have something that would say log of 1 equals 0. And if you have a base 10, you're basically saying in exponential form 10 to the power of 0 is equal to 1. And yes, that's true. Okay, so I would say if the questions 5 to 9 were pretty straightforward, I would definitely say 10 is something that's going to get you thinking a little bit more than what you did from before. Okay, let's continue on and we'll go through these last few examples right here. For number 11, there's actually multiple ways to be able to do this question, but for where we're at right now, what I would say is this: log 1000 is just the number 3. And so then 10 to the power of 3 would just be saying 1000 equals x. Now, let's revisit 11 in about 1 minute from now, because if we do question number 12, we don't know what this simplifies to, but let's say that it's going to be equal to x, just like number 11 was equal to x. And if you have something that right now, would you describe number 12 as being in exponential form or log form? Well, it's currently in exponential form. It's 7's being raised to the power of something. So if you were to undo that and turn it into log form, then you would say it would be log base 7, from that 7 right there, of x equals whatever your exponent is. And your exponent was log base 7 of 10. And this is where this question's really crazy. Now, if you look at what you have written right there, and they're equal to each other, and the left side is a log with a base 7, and the right side is a log with a base 7, then you know that they can reduce because they're equal to each other, and x would be equal to 10. Okay, I guess you can't be like the DJ and drop the base, but you could, I guess you could drop the logs, and you'd have x equals 10. All right. Not sure who drops logs, but okay. If we go back to question number 11 here, and we wanted to see what we could say with this in a different way now. Imagine if we rewrote question 11 and you said 10 to the power of a log, secretly there's a base 10 of 1000 equals x. Anytime this base is equal to this base, this 10 and this 10 are the same, your answer will be that. Now look at question number 12. This 7 and this 7 were the same, so your answer will just be that. Now, that's a log law, and it's actually going to be on your log laws that you'll see if you turn to page 34. It's written there. It's written another time coming up in your note package, but I think it's probably best to understand why this is working. But if you do want to write something on the side here, I would recommend saying something like this. What if you say a to the power of log base a of b would be equal to, well, think about it. We said if those a's are the same, then it's just going to be equal to b, and that is one of our log laws. Question number 13, it might be difficult to think about what would happen if you had 4 to the power of what equals 8. It'd be hard to do that in your head. But you could say, well, we can make our bases the same. You could say 2 to the power of 2 blank equals 2 to the power of 3. Instead of saying a box, I'll probably turn into a variable like x, and we could say, well, they both have bases of 2's, so that means the exponents are equal to each other, so 2x is equal to 3, so x is going to be equal to 3 over 2. You could do a check, but that one's a little bit strange. It's saying 4 to the power of 3 over 2 is equal to 8. And let's think about that. I'm just going to do something down here. 4 to the power of 3 over 2. Well, think back to Math 10. If you had something like that, this 2 can kick in front and you could create the square root where the 2 comes over here, the square root of 4, all raised to the power of 3. And you know that the square root of 4 is just 2, and 2 to the power of 3 is 8. So it definitely checks out, but it's probably something that you might have not been able to think of in your head right away because now you have an answer that's not an integer. Question number 14, definitely very similar in terms of the style of it. 27 to the power of, we don't know, I'm just going to call it x straight this time. 3 to the 3x equals 3 squared, bases of 3. That means that 3x is equal to 2. So x is equal to 2/3. So number 14, we have an answer of 2/3. Question 15, if you want, you could almost put a bracket around here saying that log base 3 is all has an argument of 9 root 3. Sorry if that's not super clear, but that's what it's saying. So based off of that, then you could say 3 to the power of x is going to be equal to 9 root 3. Let's change everything to bases of 3. 3x equals 3 squared times 3 to the 1/2. So that means that 3 to the power of x would be equal to 3 to the 2.5, which means that x is just equal to 2.5, or you could have also said 5 over 2. And when I'm saying x, what I'm saying is this simplifies to, this log simplifies to a value of 2.5. So if you don't say x equals, you can just as easily say the answer is 2.5. That's equal to 2.5. If I put that into the calculator, I would get an answer of 2.5. Okay, final example. If you take a look at this here, again, multiple ways to be able to do this. Honestly, the easiest way to do it would be to look at the left side and see log base 2 of 1/2 and just change that to say something like 2 to the power of -1 equals 1/2. And so if you just said -1 equals 5x plus 3, you could just do that, and then you don't even have to worry about your log at all. Now there's multiple ways to do that, but I think that's one way you could. And then you could say subtract 3, -4 equals 5x. So x is equal to -4 over 5. Sorry, it's a little messy. X is equal to -4 over 5. That is even messier. X is equal to -4 over 5. That looks better. Okay, a second way of doing question number 16 is you could have said my base is 2. 2 to the power of this exponent, 5x plus 3, is going to equal 1/2. And then you could change the 1/2 on the right side to say 2 to the -1. They have the same base, so you could just say that means that 5x plus 3 would be equal to -1/2. And then based off of that, you would subtract 3, and you could get 5x equals -4, and x would still equal -4 over 5. Okay, that's it for today's lesson on logs. It's an introduction to logs, a review of exponents. You have question number 4 on page 212 on top of that exponent review that was assigned a little bit earlier in the lesson. And that's the beginning to our unit on logs. Thanks.